Imagine that you optimize your code based on the techniques that you know about optimizing. It doesn't matter if you optimize your program, for example, using your data in a structured way to align them based on their locality, or you align your memory, or you try to reduce the cache misses. But you want to go further than that and you want to squeeze everything out of your hardware. In this video, we're talking about more detailed concepts like CPU prefetching, a technique that literally CPU thinks about what would be the next data, and based on that it does future prediction. We will look also on the page coloring, which is an OS level optimization that silently affects how memory layout across cache sets. We will also explore how Translation Lookaside Buffer will work, or TLBs as an acronym, which plays a crucial role in speeding up or slowing down your memory access. This is the ninja level performance stuff. Let's go deep into it. There are several advanced techniques that CPU uses to fetch your data and put it into the different memories, which you are not really aware of them. First technique that sounds kind of future prediction in the case of the CPU operation, which is called prefetching. Your CPU, for every data access that you have, tries to predict what you will access after that, and that includes the memory addresses that you may access after you processing your current data on the CPU, and it tries to load those data before even you ask about them. And these data loads happen between the memory and the cache, and the reason it happens is that because the memory is slow and CPU tries to help you in order to make your program faster and in order to make everything process more smoother in the shorter time. Modern CPUs come with the hardware prefetchers built in. Those prefetchers are observing your access patterns when you fetch the data from the memory and so on and so forth, and tries to understand what kind of patterns that you are using in your algorithm or in your program. If they see that you are fetching the data in a predictable manner, say for example iterating over one array, they will start pulling the data before your program asks about them. This is invisible in your code, but it happens constantly under the hood. Prefetching is one of the reasons that sequential data access is pretty fast. When you write a loop that works linearly through the array, you are making life easy for your prefetchers. But if your access pattern is irregular, like jumping around across random elements of the tree or elements of the graph, CPU cannot guess what you are doing. And in that case, prefetching will fail. You miss the cache and you pay the penalty because of it. Now here is when everything gets more interesting. Many CPUs, they have multiple types of prefetchers. Some detect stride-based patterns, others use instruction history to predict branch behavior. And sometimes, if you are using SIMD operations or memory loads in tight loops, you will get prefetching for free. But you can also help it manually. On some architectures, you can use software prefetching instructions, like built-in prefetch in C++. These instructions tell the CPU, hey, I will need this data, go get it ready before I start processing it. You can't always predict the benefit, but in some high-performance cases, image processing, neural network kernels, matrix multiplications, manual prefetching can give you measurable gains. The key takeaway is this: the more predictable your access pattern, the more the prefetcher can help you. Design your loops, your algorithms, and your memory layouts to be as regular as possible if you really want to unlock the prefetching performance and to get benefit of this powerful power in your program. Next, let's talk about something that many developers won't think about: page coloring. This concept basically lives between the intersection of your operating system and your hardware's cache layout. When you allocate a memory, like when you call malloc or use new, the operating system gives you virtual pages. These virtual pages eventually should map to the physical memory, as you may know about how virtual memory works. And these physical pages or physical memories, they're living in the RAM. Now here is the twist. Physical memory is divided into the cache lines, and those lines are grouped into the cache sets. So what happens when different memory regions get mapped into the same cache sets? They start competing. If your program is bouncing between those two regions, they will start evicting each other's cache lines, even if you're only using a small amount of data. This is called a cache conflict or a cache alias, and it is a silent performance killer. Page coloring is the OS way of avoiding this issue. It tries to spread out physical pages across different cache sets. We can call it different colors, so that data in different regions won't step on each other. If the operation system is smart, it distributes memory in such a way that each part of your program gets its own dedicated slice of cache. The problem is that you as a developer cannot see it. You don't know which physical page you are getting for your program. And in systems without page coloring, or by disabling it specifically, you might be getting unlucky. Let me give you a real-world example. Suppose you allocate two arrays, one for input, one for outputs. They are the same size, and you alternate reading from one and writing to the other. If they happen to land to the same cache set, they will start to kick each other out of the cache, and because of it the performance of your program drops. But if the page coloring spreads them apart, you suddenly gain performance without changing your code at all. So what can you do? If you are working in a performance critical domain, test your allocator, use huge pages, or align allocations. In some systems, you can even use custom allocators, which are aware of physical addresses. But even in everyday code, by knowing that cache conflict can happen in this level, helps you find a clue why your program performance drops, or to find a way to improve the performance of your code. Now let's talk about one of the underrated performance factors in modern memory systems, the TLB or Translation Lookaside Buffer. Remember how virtual memory works? As we talked in the previous videos, which I put a link to here or here, every virtual address of your program must be translated into the physical address. That is how the operation system isolates processes and manages memory efficiently. But these kind of translations are not free. The operation system uses a data structure called page tables to track this kind of mapping that it has. And walking through the tables can take time, especially if it involves multiple levels. To make it faster, CPUs use a cache specifically for page table entries, and that's a TLB. It stores recently used virtual to physical memory translation so that the CPU doesn't walk through all the table layers or all the table levels on every access. If your address is already in TLB, it is an instant act for the CPU. If it's not, then you will get a TLB miss, and the hardware has to go looking for it. Now here is the catch. The TLB is small. Typical x86 processors have only a few hundreds of entries in their TLB. It means if you access a huge datasets like a massive matrix or a scattered hash table, you can easily exceed the TLB size. Every time that happens, you get a miss, and every miss is a microsecond delay. You can spot this in the perf output. If you see high TLB miss rates and long memory stalls, you're probably walking through the many pages. There's a fix for that. You can use huge pages. Normal pages are 4 kilobytes. Huge pages are 2 megabytes or even 1 gigabyte. With huge pages, one TLB entry covers a much larger region of the memory, which reduces such misses dramatically. Many operating systems support transparent huge pages or THP, which means you can get this benefit automatically, though the implementation and reliability can vary. Another way to reduce TLB misses is to keep your data compact and contiguous. Fewer objects, less fragmentation, tighter memory, which is equal to fewer page translations. TLBs are the secret middleman of the memory access. They don't get as much love as caches or prefetchers, but they make virtual memory efficient. And when they fail, performance collapses. Respect your TLBs. What we talk about today is the real next level of memory understanding. And this is the stuff that separates decent performance from great performance, especially when you're operating near the hardware. Prefetching lets your CPU anticipate your needs. If you write your access pattern clearly and predictably, you can get free performance from the hardware that is literally trying to guess your next move. Page coloring is a silent background process that can make or break your cache performance. When you control memory layout, or at least test it, you gain insights about cache collisions you never saw coming. And TLBs, they are the heroes of virtual memory. If you are constantly switching between in scattered pages, they will slow you down. But if you help them out by using huge pages or compact structures, they will reward you fast, clean translations. If you have enjoyed the deep mechanics of how hardware and memory systems work together, don't forget to like the video and subscribe to the channel. And if you want a follow-up video with benchmarking prefetchers or simulating cache aliasing, let me know in the comments. Until the next video, good morning, good afternoon, and good evening. Bye.